So we divided polynomials in a prior section, and now we're going to expand that with a couple of theorems called the remainder theorem and the factor theorem. And I think it's best maybe that I give you an example of this to kind of exemplify, so you don't get lost here in the abstraction of it. So the remainder theorem says if f of x is divided by x minus c, then the remainder is f of c. Okay. For example, let's say we have f of x being x squared minus 4, right? And we know x minus 2 and x plus 2 are factors, right? We know x minus 2 is a factor. Let's say we didn't know what the other one is. So it's kind of like if I have 8 and I know 2 is a factor, then couldn't I divide 8 divided by 2 and get the other factor, right? Because 2 times 4 is 8. Or 8 divided by 2 would give me the other factor. Well, let's go ahead and take that x squared minus 4 and let's divide it by x minus 2. So if I went and did some long division and I divided it by x minus 2, right? And I'm trying to match x squared, x times x squared, x times negative 2, negative 2x. Don't forget to change those signs. Now I'm matching the 2x. So plus 2, 2 times x, 2x, 2 times negative 2 minus 4, change those signs. And look, I have no remainder, right? I have no remainder. So what this is saying is, this remainder theorem, if I'm dividing by something of the form x minus c, in this case x minus 2, right? I'm dividing by x minus c, so our c is 2. Then f of 2 would give me my remainder. That's my remainder. See it right there? There's my remainder. 0, right? So that's what the remainder theorem is saying. And then the factor theorem is saying, well, if the remainder is 0, like this scenario, right? If the remainder is 0, then x minus 2 has got to be a clean factor, right? And it was. We knew that. We knew x minus 2 is a factor of x squared minus 4. So let's go ahead and use the remainder theorem for this next one with a different function, 2x cubed minus 4x squared plus 5x minus 3. Let me go ahead and erase this in a sec. So here's our function f of x, and we're going to test if x minus 2 is a factor, right? And let's find f of 2 first. Let's see if it has a remainder first. So let's plug the 2 in. Let's see what the remainder is. So we got 2 times 8, 16, minus 4 times 4, 16, plus 10 minus 3. Looks like those are gone, so it's 7. Right? In other words, this is saying if you took 2x cubed minus 4x squared plus 5x minus 3, you divided it by x minus 2, then you're going to get down here a remainder of 7. Right? That's what it's saying. Well, if the remainder is not 0, is x minus 2 a factor then? No, right? This remainder's got to be 0. Right? So no, it's not a factor. So x minus 2 is not a factor. Right? Because you got to have a remainder that's 0. Otherwise, it's not a clean factor. All right, let's keep going here. We got the next one here. Let's go ahead and decide if f of negative 5 is f of negative 5. So we got 2 times negative 5 to the 4 plus 12 times negative 5 cubed plus 6 times negative 5 squared minus 5 times negative 5 plus 75. And if you punch that all in, I'll save us a little bit of time. This does equal 0. It does equal 0. So the remainder is 0. So this is saying for this function, this fourth degree function, it hits at -5, 0. So -5, if -5 is a 0, then x minus that number is a factor. Okay, if you have a 0, then you know one of the factors. So what we're going to do is we're going to go ahead and do the division. We're going to take f of x being 2x to the fourth plus 12x cubed plus 6x squared minus 5x plus 75. And we're going to divide it by, we know -5 is a 0, so x minus -5 is a factor. And we're going to find the rest of this. Again, it's kind of like if you had 9 and you know 3 is a factor of 9, then you could go 9 divided by 3 and you could find the other factor. Oh, it's 3, right? That's what we're doing here. We're going to take 2x to the fourth, blah, 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 and we're going to divide it by x minus -5. But what we're going to do is we're going to do it with synthetic division. So -5 is our 0. That's our c, x minus c. And then we're going to take the coefficients of that 2x to the fourth. So we have 2x to the fourth, 12x cubed, 6x squared, -5x, and then the 75. And we already know it's a 0, so when we do this division, I better get a remainder that's 0 on this, or I did something wrong, because it already told me it's a 0. Drop the 2 down, straight down, 2 times -5, 12 minus 10, 2 times -5, 6 minus 10, -4 times -5, -5 plus 20, 15 times -5. There it is. And then these are the coefficients of the quotient, right? So 2x 1 degree less, 2x to the third plus 2x squared minus 4x plus 15, right? So again, is -5 is a 0? You bet it is, because it had a remainder that was 0, right? We'll continue on with these types of problems here. Let's go with this one now. We're going to actually solve this equation. So we're going to have to factor this. So it's given us 2x cubed minus 3x squared minus 11x plus 6 is 0. So it's saying -2 is a 0 of this function. -2 is a 0. Hits right there. Well, if -2 is a 0, then x minus -2 would be a factor. Then x minus -2 would be a factor. And I can go ahead and do the division now. So -2, that's my c, x minus c. And now I'm taking these leading coefficients. 2, -3, make sure it goes down by a degree, and 6. And I should have a remainder of 0 because they told me -2 is a 0. Drop it down. 2 times -2, -3 minus 4, -7 times -2, -11 plus 14, 3 times -2, 6 minus 6, 0. There it is. So that's the coefficients of my quotient. So 2, 1 degree less than x to the third, 2x squared, minus 7x plus 3. So here's what we have so far. X minus -2, x plus 2. Now I'm factoring 2x squared minus 7x plus 3, which will factor into 2x and x. That'll be 1 and 3. That's going to have to be minus minus. So 2x minus 1, x minus 3, and this equals 0. Now it's completely factored. So we can solve the equation. We can find all the zeros for this. -2 plus 1 divided by 2, add 3, add 3. There's all my zeros. That function. This is saying it hits at -2, hits at 1/2, and it hits at 3, right? And this is 2x to the cube, so I know it's going to go down to the left, up to the right. If you were actually graphing this, it would look something like that, right? If you were graphing the original cubic function on that. Okay? All right, the rational zeros theorem. This is handy when you're starting out and you're not given any zeros because you can make a list of possible zeros. possible zeros. And so it'll be factors of the constant over factors of the leading coefficient. Okay, so number one, let's list the possible rational, that's the term for rational zeros. So it'll be factors of the 8 divided by factors of 3, right? So if you think about factors of 8, you could have, 1 times 8 is obviously 8, right? So positive 1, positive 8. But isn't negative 1 and negative 8 also factors of positive 8? So it's got to be plus minus on that. Negative 1 times negative 8 is obviously a positive 8 as well. And then, of course, 2 and 4, right? And it's the same thing, plus minus on those. And then it's going to be over those ones over factors of 3. Well, factors of 3 are just 1 and 3, plus minus, plus minus. So let's go ahead and list the possible rational zeros now. So factors of 8, I'm going to start with the smallest factors of 8 first. I'll go 1, and I'm going to go over 1 every time. And then I'll go 2 over the 1. Then I'll go 4 over the 1. Then I'll go 8 over the 1. So 1 over 1. And then the other factor of 8, which is 2. Next factor of 8. Next factor of 8. And now I'm going to do it, each of those factors of 8 over the 3 this time. So plus minus 1 over the 3, then the 2 over the 3, then the 4 over the 3, and then the 8 over the 3. Okay, and these are all possible rational zeros here. And once we have, well, for this one it's just asking us, just go ahead and list them. So that's all we got to do on this one. There's our list. Call it good. On the next one, what we're going to do is we're going to use a list, use the possible rational zeros. So to find, we'll use those rational zeros to find the zeros. This next one. So here we go. Let's make our list first. So possible rational zeros would be factors of 20 over factors of 1. So factors of 20, you got 1 and 20, of course, plus minus, 2, 10, 4, 5. Factors of 1, you just got 1 and 1, right? So let's go ahead and start our list. I'm going to go, it's always over 1, so plus minus 1 over 1. Next factor of 20 would be 2. Next factor of 20. Next factor of 20. And then the 10 over 1, and then the 20 over 1. Okay, so here's our 12 possible zeros. What we're going to do is, right, this is a third degree, so I could have up to 3 of these work for us, right? There are 3 zeros, we just don't know if they're all real zeros, but this is our list of 12 that we got to test. So the first part is, let's go ahead and test, let's start with negative 1. And then see if negative 1 works. If negative 1 doesn't work, then we'll try 1, right? We're going to see where this hits. So here's our function, f of x equals x cubed plus 8x squared plus 11x minus 20. And we're going to see if, is negative 1 a 0? Does it hit at negative 1? Well, if negative 1 works, then x minus negative 1 is a factor, meaning it'll have no remainder when I do the division of that one divided by that one. All right, so I'm going to divide x cubed plus 8x squared plus 11x minus 20. I'm going to divide it by x minus negative 1. So negative 1 is my c. Leading coefficients, 1, 8, 11, negative 20. And I'm going to see if my remainder is 0. That'll tell me if negative 1 is a 0. In other words, if x minus negative 1 is a factor. Drop the 1 straight down. 1 times negative 1, negative 1. 8 minus 1, 7. 7 times negative 1, negative 7. 11 minus 7, 4. 4 times 1, negative 4. Uh-oh. Is my remainder 0? No. So is x minus negative 1 a factor? No, it's not. So I'm throwing out negative 1, right? So negative 1 is out. So let's try positive 1. So that one's out. Let's try positive 1. Well, if positive 1 is a factor, I'm sorry, if 1 is a 0, x minus 1 would be the factor. So let's try 1 now, and let's do the division. X cubed plus 8x squared plus 11x minus 20 divided by x minus 1. And we're trying to see if this has a remainder of 0. Drop the 1 straight down. 1 times 1, 1. 8 plus 1, 9. 9 plus 1, 9. 11 plus 9, 20. 20 times 1, 20. Negative 20 plus 2. Hey, there you go. So it works. So 1 is a 0. So x minus 1 is a factor. And I'm going to go ahead and put these as my coefficients of my quotient here. So started with an x cubed now, so it's 1 degree less. So 1x squared plus 9x plus 20. And now the nice thing is I have a quadratic at this point, so I can just factor this thing straight up, right? So x squared plus 9x plus 20 factors into 4 and 5. And now I can find all my zeros. X equals 1, negative 4, and negative 5. And notice all three of those, 1, negative 4, and negative 5, those were all listed. 1 was there, negative 4 was right there, and negative 5 was also listed right there. So sure enough, I had 3 zeros. They were all real zeros, and they were in our list, right? And we were kind of lucky that we hit one of them right off the bat after the second try, right? The last part just says use the zeros to factor it. Well, you already have it factored right there. I do that all at the same time in the process. So just list it in factored form right there. Okay. All right, let's look at this next one. Similar process here. Number 1, let's list our possible rational zeros. So we have factors of the constant term on the end, the 6, factors of 6 over factors of 3. So factors of 6, I got plus minus 1 and 6, I got plus minus 2 and 3. Factors of 3 is just 1 and 3, right? So I'm going to do all of them over the 1, and then I'll do all of them over the 3. Okay, I'll do all the factors of 6. So plus minus 1 over 1, plus minus 2 over 1, plus minus 3 over 1, plus minus 6 over 1. And then I'll do all of those 1 over 3 now. Next factor is 6 over 3. Next factor is 6 over 3. Next factor is 6 over 3. I do need to check and make sure, do I have any repeats here? As I sure, 6 over 3 is 2, right? I already listed 2. 3 over 3 is 1. I've already listed 1. So it looks like I only have 12 potential rational zeros here. 12 potential rational zeros. So let's go ahead and start our process of finding the zero. So here's our original. And let's go ahead and test. Let's try 1 first, then we'll try negative 1. So we're trying to see if 1 is a factor. If 1 is a 0. Well, if 1 is a 0, then x minus 1 is a factor. And so we're going to go ahead and divide 3x to the 4th, blah, 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 divided by x minus 1. So 1 is our C. 1 is what we're testing. 3, negative 11, negative 1, 19, and 6. And let's see if this gives us a remainder of 0. Drop the 3 down. 3 times 1, 3. Negative 8. Negative 8. Negative 9. Negative 9. 10. 10. Oh, that doesn't work. I don't have a remainder of the 0. So let me throw out 1. 1's no good. Let me go to my next one. How about negative 1? Let's see if negative 1 works. Well, if -1, if it does, this one's no good. If -1 works, right? -1's a 0. Then x minus -1 is a factor. That's what we're claiming. Let's test it. -1 plus 14, 13. 13, 19 minus 13, 6. 6 times -1, -6. Hey, there we go. It's a 0, right? It's a 0. It has a remainder of 0. So x minus -1 is a factor, and I'm going to go ahead and put in 3x, 1 degree less, to the third now, minus 14x squared plus 13x plus 6. So that's how far we are so far. Now it's a third degree. It's not a second degree. So I'm going to have to repeat this process again because I can't just straight up factor that x cubed, right? And sometimes, if you guys remember, sometimes you just touch at a 0, which means you have even multiplicity, right? So you really should check to make sure it's not a repeated 0. So let me see if x minus -1 is a factor again. And I'm going to take that one divided by that one. So let me test -1 again. This time I got 3, -14, 13, and 6. I got to make sure it's not a repeated 0. Okay? But after I check it out again, well, let's see what we get here. Drop the 3 down. 3 times -1, -3, -17, 17, 30, -30. Okay, that's what, -24. Okay, it's not a repeated 0. So it's not a repeated 0. So I can move on from -1, right? So what we have is the x plus 1. Now I got to test something else. Let's move to 2, our next one. Let's try 2. So plus minus 1, plus minus 2, right? See if 2 works. Well, if 2 is a factor, then, I'm sorry, if 2 is a 0, then x minus 2 would be a factor. And we're going to take that one divided by x minus 2. And we're going to see what we get. So 2 is our C. 3, -14, 13, and 6. Let's see what we get. Drop the 3 down. -14 plus 6 is -8. -16, -3, and 2 times -3, -6. Hey, it works. No remainder. So that's 3, 1 degree less, x squared minus 8x minus 3. And then we can, now it's a quadratic, so we can go ahead and factor that. That's 3x and x. That'd have to be 1 and 3 here, minus. Let me check that. 3x squared minus 9x. Oops, that's got to be a 3x squared minus 9x plus x minus 3. There we go. And there's all my zeros. -1, 2, -1/3, and 3. Look at that. All 4 of my zeros are right there. And we've already factored it. So now I just write the factored form. Right there. All right, let's move into this next one here. So we've got a 4th degree polynomial. Let's list our possible zeros, which are factors of 4 over factors of 1. Possible rational zeros, factors 4 over factors of 1. So it'd be plus minus 1 over 1, plus minus 2 over 1, plus minus 4 over 1, right? Now we're going to test them. So we've got this. Here's our function. Minus 4x minus 4. And let's try -1 first. Let's see if -1 works. Well, if this crosses at -1, then x minus -1 must be a factor, right? X minus -1. So let's test it. So let's go ahead and do the division. Does -1 work? So I'll have the leading coefficients 1, 4, 3, -4, -4. 1 comes straight down. 1 times -1. 4 minus 1. 3 times -1. 0. -1 times -4 is 4. 0. looks like -1 works, right? And we have 1x cubed plus 3x squared plus 0x minus 4. So that's what we have so far. Let's make sure it's not a repeated 0. So let's test it again. Let's test -1 again and see what we get. So now I'm doing this divided by that. So I'm going to test it to make sure 1, 3, 0, -4. Let's just make sure it's not a repeated 0. Bless you. 1 times 1, or 1 times -1, 3 minus 1, 2, 0 minus 2, 2. Okay, it's not. See how that remainder is not 0? Okay, so it's not a repeated 0. So we can be done with -1. So far we have x plus 1, one of those factors. Now I got to test another one. So we're done with 1. I'm sorry, we're done with -1. We're done with -1. Let's try 1. Just the regular old 1. Let's see if it hits here at 1. Well, if 1 is a 0, x minus 1 is a factor. And we're going to take that x cubed plus 3x squared plus 0x minus 4. We're going to divide it by x minus 1. So 1 is the proposed 1, 3x squared, 0x minus 4. Let's see if this works. 4, 0 plus 4, 4 times 1, 4. Oh, it does work. So it'll be 1 degree less than x to the third. So 1x squared plus 4x plus 4. So now we have x plus 1. X minus 1 was also a factor because 1 is a 0. And now we can just factor this x squared plus 4x plus 4 because we've got the quadratic and it factors real nice for us. X plus 2, x plus 2. So here's our zeros. -1, 1, and -2 with multiplicity of 2, meaning it just, right, so it hits at -1, it hits at 1, and it touches at -2. It's going to touch from the bottom or from the top. It's going to cross through these points one way or another, right? This is an x to the 4th, positive x to the 4th, so I actually know it should go up to the left and up to the right. So it'll look something like this. It's going to have to come down and cross through, and then eventually it's going to have to cross back up. And of course, this should be smoother than that. But anyways, you kind of get the idea. You'd have to plot some points if you were actually graphing it, right? And since we found the zeros, we actually have this already factored. So now we just got to write it. X plus 1, x minus 1, and x plus 2, x plus 2. Well, there's 2 of those x plus 2s, so we're going to say it as a quantity squared there. Okay. We have, in this scenario, they give us a 0. So you're given this f of x equals 12x squared cubed, plus 13x squared minus 1, and they give us one of the zeros. Let's go ahead and start with listing the possible zeros first, just like we did on the other one. So it'll be factors of the 1 on the end over factors of that leading coefficient 12. So you got plus minus 1 over 1, plus minus 1 over 2, plus minus another factor of 12 is 3, another factor of 12 is 4, another factor, 4, another factor is 6, another factor is 12. Okay, so here's all our possible rational zeros. And notice they gave us f of 1/4 equals 0. So they're telling us this thing hits at 1/4, right? So they're telling us that one is a 0. So they're like, hey, we're starting you on this one. We're going to give you a little hint here instead of blindly working the problem. So if this is our function, here, let me write it. F of x, 12x cubed, 13x squared. Notice there's a 0x, there's no x part, and then minus 1. And they tell us 1/4 is a 0. So x minus a 4th must be a factor. So let's do the division. 1/4, I got 12, 13, 0x minus 1, and they tell us this is a 0, so I better have a remainder that's 0 or I did something wrong here. Drop the 12 down, 12 times a fourth, 12 fourths is 3, 13 plus 3 is 16, 16 fourths, 16 times a fourth is 4, 0 plus 4 is 4, 4 times a fourth is 4 fourths or 1, and negative 1 plus 1 is 0. Sure enough, it is a 0. And now we can put in that 12x 1 degree less squared plus 16x plus 4. And notice that I can take a 4 out of that. Take a 4 out of that, and I'd be left with 3x squared plus 4x plus 1. And I'm actually going to put that 4 into that one so I don't have rational numbers. Just have integers there. And then I'm looking at this 3x squared plus 4x plus 1, and the nice thing is I got a quadratic again, so this will factor for us. So those are my 3 zeros. Third degree's got 3 zeros. And we already factored it. So let's go ahead and write the factored form. 4x minus 1, 3x plus 1, x plus 1. There's our factored form of that. All right, the last part of this is we're going to talk about this intermediate value theorem, which says if A is less than B and f of A and f of B have opposite signs, then f has at least 1 0 in the interval. So here, let me kind of scratch this out. So let's say you have some A right here and some B right here, okay? And if another way to say that is if there's some value k in between here, okay, so you have some f of A here, f of B here, and let's say our k is 0, okay? And this is a polynomial, so you know it's continuous, smooth and continuous. Then what the intermediate value theorem says is it says there must be some c value in between A and B such that f of c equals k, right? That's the c value right there, somewhere in between there. So if it goes from a negative to a positive, in other words, right? If I'm going from a negative to a positive, I got to cross. I must have a 0 somewhere between A and B. Does that make sense? And same thing if it goes from positive to negative, it's saying the same thing. But formally stated, another way to say this, the intermediate value theorem, is if you have A less than B and there's some k between them, then there exists some c, there exists a c in between A to B such that f of c actually equals k. We're just looking at it for k being 0. It doesn't have a 0. So like for this first one, it says, well, how about for 12x cubed plus 13x squared minus 1? How about for that one? Well, let's find, what does f of 0 equal? Let's find out. Does this thing switch signs from 0 to 1? Negative 1. Okay, so f of 0 is negative 1. So this is saying I hit right here. Now let's go ahead and find f of 1 is the other end of the interval, right? I'm going from 0 to 1. So it looks like I got 24. So f of 1 is way up here. I got 1 comma 24, right? Well, this is a polynomial, so it's got to go through smooth and continuous. So we know, oh, it's got to hit, right? The intermediate value theorem is guaranteeing the existence of a 0. So since f of 0 is negative and f of 1 is positive, they change signs, there must exist a c in that interval such that f of c is 0, right? That's what we're saying. We're guaranteeing, yes, there's got to be a 0 between them, right? Somewhere between 0 and 1. We don't even care what it is, right? But as geeky mathematicians, we just care that it exists by the intermediate value theorem. Right? Let's try one similar. How about for this function from 1 to 2? So we throw in 1. Let's see what 1 gives us. Okay, so f of 1 is 8. So I'm going from 1, 8. Well, now I'm going to plug 2 in. So as long as 2 is negative, I know it crosses the x-axis. So I must have a 0, right? So it's got to go from positive to negative. It's got to change. Well, let's check it. What does f of 2 give us? Oh, 16. Well, f of 2 is way up here at 123. 2 comma 123. So we don't know. We don't know that it has a 0. It did not tell us that it has a 0. It does not guarantee the existence of a 0. So since f of 1 and f of 2 are both greater than 0, they're both positive, no conclusion can be made from the intermediate value theorem. About zeros on that interval, at least on that interval, right? Doesn't really help us. That's it. That's the intermediate value theorem in a nutshell. Thanks for watching.